As we've begun to explore more and more of the genetic diversity in biological organisms and get a better idea about genomes, about their structure, and then even expand that to a population level, we've gotten a lot of surprising outcomes, some things that we didn't quite expect. One of which we covered in 3.1, was the amount of non-coding DNA in our genomes. And so as people begin to examine this, they begin to map the genes and know exactly how much of our genome is coding and exactly what parts of the genome have an impact on phenotype and what don't. They begin to reevaluate their ideas about evolution. And this is one of the, maybe the most dramatic, unexpected thing to come about in the field of evolution as we incorporate this massive amount of information about genomes. And this is the idea of neutral theory. Now, I've already given you in class, before the whole coronavirus took over our lives, a Dr. Terry's overview of mutation and which mutations, in general, kind of a general rule, what happens when a mutation occurs. And there are three outcomes. Is it good? Is it bad? Or is it neutral? And if you remember right, on that graph, I had a diagram that showed about, I don't know, I think I usually put like 95% of all mutations that occur are effectively neutral. And that's my own number. I don't know that anyone's ever estimated it, but there are some good reasons as to why the vast majority, certainly we can say that, the vast majority, at least 80%, maybe 95, even 99%, of all mutations, when they occur, are effectively neutral. Their variation, their diversity, but they don't negatively or positively impact the organism that's carrying them. And so this is a dramatic change from the way that we were looking at genetics and evolution of species before we understand their genomes. So Muto Kimura, a Japanese researcher, came up with this idea, and he basically said this: 95%, most of the mutations, the variation that we see in the population, good isn't bad, it's just diversity, it's just there. Okay? So let's look at the reasons why the vast majority of mutations are neutral. The first one we've already covered, so you should remember these 5 examples. Number 1, most DNA is non-coding. Now, just because I say non-coding doesn't mean it has 0 impact on phenotype. However, in the non-coding DNA, the phenotype impact is much more diffuse. It's spread out over a massive area. And so although we can have a mutation in non-coding DNA that is incredibly bad for an organism or is incredibly good for an organism, the chances are it's going to be neutral, just kind of playing the odds. So non-coding DNA is a really excuse me, I just have something caught in my throat. I'm not sick, I promise. Don't take me away. Anyway, sorry. The vast majority of mutations in non-coding DNA are neutral just because the phenotypic impact. And so we've looked at this already, right? Most of our genome is either transposons, roughly 50%, or introns, and then a few other categories. Structural chromosome, like heterochromatin. Some of these duplications do have an impact, but by and large they're neutral. But there are other reasons also beyond just the non-coding DNA. And if you think back to the genetic code, you already know one of these, and some of them you may have come across or even guessed. So number 2, non-synonymous mutations with minimal fitness impact. So remember, a non-synonymous mutations means that we've changed the protein. So sometimes mutations occur, they change the protein, but yet there's still no overall impact on fitness. There's still diversity. So for instance, here is a enzyme that interacts with ATP. The red areas are areas that are very, very conserved, meaning that when mutations occur there, they're almost never kept and we see very, very little diversity. But the blue areas have very high levels of genetic diversity, meaning mutations occur there all the time and they're often kept because they're not good or bad, they just build up and there's just diversity there in the population. Okay? Eye colors may be an easy one, right? If I have brown eyes and I have a child that carries a new mutation that makes them have green eyes or blue eyes or a different shade of brown, how does that impact their fitness? And in the human population, the answer is probably, at least in most cultures, 0. Might be a little better, a little worse, but effectively, it's not good or bad. So just because the protein itself changes doesn't mean it's going to be an advantage or a disadvantage. It can still be effectively neutral. And of course, synonymous mutations within the coding region, right, especially at that third position, mean that we're going to have, by definition, a neutral mutation. It's not good or not bad. DNA carries it. We can identify it if we sequence the genome, but it has no impact at all on the phenotype of the organism. And then finally, effective mutation. So we're going to throw this in here, and really this is kind of gray area, borderline, but it works well. This is saying that if a mutation occurs that does change the phenotype of an organism, but it's not significant enough to make a huge difference, then we could basically treat it as if it was effective, right? This is kind of like saying, hey, do you want me to give you $100 or $101? And the answer is, well, I really don't care. Either or is fine. It really doesn't make a difference to me. And although there is a difference, it's not significant enough to play a major role in what's going on. So effective neutrality, just maybe as an example. Let's say you have a mutation that makes you a little bit taller. And maybe that's a good thing. You can maybe compete for mates better because you're bigger, or you can reach fruit higher in a tree. But in the long run, it might mean the difference between, on average, having 5 offspring and having 5.1 offspring. So in the long run, that might be an insignificant amount. Okay. Now, one of the inevitable outcomes of this is if we can treat the vast majority of mutations and thus the diversity that we see in our genome, if we can treat it as neutral, that means there are some really interesting and cool extrapolations. And originally you might think, oh, if it's neutral, then that's completely unpredictable. There's nothing really that we could do. But in reality, it's kind of the reverse, at least in large scale. So let me give you an example. Okay, we're going to go back to the simulator here. I might have to bring it up. There it is. Okay, so if I said, hey, I'm going to do a neutral mutation, not good, not bad, everything's the same fitness level, we're going to leave everything identical, and then we're going to run this, and I'm going to say, for any one of these simulations, are we going to fix the big A allele like that one, or the little A allele like that one? And again, from what we learned, it's 50-50. And so if I ask you, say I run 3 of these, what's the outcome? You're going to say, oh, wow, I've got a large margin of error. It might be all 3 go up. It might be 2 out of 3 go up. There's a number of fairly probable outcomes with only 3 simulations. But what if I said, and I'll spare you this, but what if I said I'm going to run this 1,000,000 times? And wait for fixation. Now, we've got a little bit of a biased sample here, right? But again, it's like if I flipped a coin. Sometimes you flip a coin 6 times, you get 5 heads or 4 heads, right? But if we did it 1,000,000 times, then all of that's going to even out. So it's actually quite predictable when we have a large enough sample. You could predict that would be close to 50-50. Maybe a little bit off, a little bit higher, a little bit lower. And we could even do some statistical calculations to figure out about how much we would expect to be off and still be in that predictable range. Okay, so just be aware that even though we can't make individual predictions, neutral theory means that in big populations, in big samples, that it actually is very predictable. And in fact, this is the same law of probability that casinos rely on. So if casinos know the rules of a game, they know it exactly, they can make it so that they, as long as enough people play, they always make money. It's a great job to be in the casino. So if you know the rules and know exactly how it works, and you can say that, we're going to set up the rules on the roulette table so that, we have a overall 3% advantage, then all you have to do is have as many people come in and play, and as long as that general rule holds true, you're always going to win over a big sample. You might lose some of the time, but if you know the rules, you're going to win that 3% of the time. Okay? So one of the predictions of neutral theory is this idea of coalescence, or we could call it coalescent theory. So this is a diagram looking at a small population and how they pass on their alleles. So every little box here represents an individual. The 2 dots represent their alleles. And notice some individuals don't pass on their alleles. They either don't reproduce or their offspring die, so the next generation doesn't have any of their alleles. Now, we realized early on that we don't need to treat these alleles as stuck together because of random assortment. We can treat the alleles completely independently. And so notice this is the exact same diagram as this one, but just with alleles rather than individuals. Okay. And what you'll notice is that if we trace it back, so this is a simplified version where we're only tracing back the ones that don't die out. Okay, and so when we do that, inevitably all of the diversity that is represented in today's population goes back to a single allele. So notice all of the alleles in this final generation go back and they coalesce. Coalesce means merge together. In this case, merge together in the past. So there is the coalescent event, or the single allele that gave rise to all of the descendant alleles. This would be like mitochondrial Eve. Now, notice that just because there's a single ancestor doesn't mean there weren't other individuals alive at that time also, and half of them would have been females. But because just by chance some of these lineages die out, they don't get represented as much, and there's no natural selection here. So coalescence is inevitable. In a way, it's kind of like saying, hey, let's flip a coin, and let's do it 10 times, and then we'll get an outcome. And if it's biased a little bit, then we'll bias the coin for the next 10 flips, so it's 60% of one and 60% the other. So if we do that, we're going to get fluctuation back and forth, but eventually we'd have a coin that could only flip heads. So that's what happens with these fixation of alleles. Eventually you get a single allele, and that, you get fixation, you get a single allele. Now this may not even be fixation, because realize along this pathway we might have had new mutations build up, so there still might be some diversity. This doesn't mean every allele is identical here. Some diversity would have built up, but notice that despite new mutations being possible, we still have a single ancestral allele, and that's coalescence. Okay? So we could measure the average time to coalescence. Now sometimes, because there is unpredictability here, sometimes it might be just, it's like flipping a coin. Sometimes you bias it a little bit, or it might be a little short, a little bit long. But over time, if we have enough of these samples, we could look at many different genes in one population, or we could look at many populations. All that randomness will average out. And it turns out that we can very easily predict the average time to coalescence. Now this is in diploid, sexually reproducing populations. If it wasn't, that 4 would have to change, but it's still going to be proportional to population size. So the only thing that impacts the average time for coalescence, and this is if it's evolving neutrally. We'll look at natural selection here in just a little bit. But if it's evolving neutrally, the only thing that affects the average coalescence time is population size. And so notice that in large populations, if we have 1 million individuals, on average it's going to take 4 million generations to have coalescence occur. Okay? But if we had a smaller population, 10,000 individuals, it might only be 440,000 generations for coalescence on average, and some are going to be a little faster and some are going to be a little slower. Now, if natural selection is working on a population, or if the population size is expanding and contracting, then we've got a little bit of a different situation. So notice coalescence time in a larger population is going to be longer. In a smaller population, it's going to be smaller. Now, I'm not going to ask you to memorize this. I'm not going to have you plug it into an equation and say, if we have 1 million individuals, what's the average coalescence time? The answer would be 4 million, as long as the population was sexually reproducing and diploid. But that's not important for this class. Okay? Yeah, that little thing in my throat won't go away. Anyway, you don't need to know that quantitatively. Just know it in theory, that the bigger the population, the longer the coalescence time is. And what that means is we're going to have more diversity in larger populations also, because we don't get loss of diversity through this coalescence process. If populations shrink or grow, then that average coalescence time is going to be affected also. Okay? Now, if there's natural selection, we can have a variety of effects. Neutrality, we can make predictions in large populations. If there's positive selection, that's going to greatly speed up the rate at which we fix the beneficial allele, right? If there's balancing selection, then we're going to maintain diversity for much longer than we maybe would normally expect because of balancing selection. If we had something like, say, overdominance, which maintains both of those alleles in the population. So, what determines the average heterozygosity of a population? Well, it turns out that there's this really interesting impact. So for short periods of time and looking at specific cases, we need to take into account both the mutation rate and the population size. Now, this is a neutrally evolving site, so we're going to eliminate natural selection by not worrying about those things that are under strong natural selection. We'll only look at the 95% or so of the genome that's evolving neutrally. And so for limited cases, we need both mutation rate and natural selection. However, what people realized, and we've got this here on the next slide, what people realized is that the population size actually cancels itself out. And here's why that is. In large populations, we do have many, many more mutations. However, fewer of those mutations become fixed. So this population size kind of balances itself out. Big population, more mutations, but also smaller chance of fixation, and vice versa. In small populations, we have fewer mutations, but it's much more likely that they are going to be fixed in the population. So it works itself out. And so really, in the long run, if we're looking over long, long periods of time, the only thing that we need to look at when we're looking at neutral evolution is the mutation rate. And that can then be a nice prediction for long periods of time and the amount of diversity that we'll see in a population. Now, people also realize that we could look at the mutation rate and the amount of diversity that's building up in a population as an estimate of time. So for instance, if I know that on average every 10 generations there's a new mutation fixed in a population, then all I have to do is look at the difference between two populations. Let's say we look at lions and tigers. We align their DNA, we count up all of the differences that occur, and then we use that as an estimate of how much time has passed. So by doing that, we can get actually very, very accurate estimates for divergence times between different species. And this process is called the molecular clock. Okay? So the molecular clock is simply just using the amount of diversity between two populations, or in some cases even within a single population, and looking at that diversity as a measurement of time elapsed. And that only works for neutrally evolving sites, right? If there's been natural selection working on a site, then you'd have to take it on a case-by-case basis, and you couldn't make a general rule that applied to everything. Okay? And so mutation rate is key, and we can use that to estimate time of divergence in a molecular clock. Okay? And so you can think of the molecular clock a little bit like a random event, much like shark attacks or meteorite strikes. And if I was to ask you tomorrow how many people are going to be killed by sharks in the United States, say, you would have a really hard time answering that question. You could say, well, maybe 1, but most likely 0, but we can't tell you precisely. But if I said, well, here's the data, how many people are going to die in the next 4 years? And then you could say, oh, well, on average, we have X number of people that die each year from a shark attack. So we just average that over 4 years, and we'd maybe be pretty close. And if it was over longer times, as long as our data that we're using to make the estimations was okay, we would be very, very accurate. Okay? And so whether it's shark attacks, meteorite strikes, lottery odds, they are unpredictable in the short term, but over large sample sizes and big periods of time, they're actually very, very predictable. And so we can use that to our advantage. So there are some issues with this. We have to have good data to base these estimates off of. And so there are some problems with using these data to estimate divergence time, for instance, like in a molecular clock. The main issue here is saturation. So notice that when I do an alignment of DNA and I measure all the differences, I'm assuming that every time I see a difference, that represents one mutation. But realize that as time goes on, that one mutation rule may not be necessarily true. So here's an example. So notice there's a single mutation where this ancestor had a T there, but then there was a mutation that occurred, and then there's an A. And so now we have a 2. So far it's a very good estimate. So 2 mutations, and we see 2 differences between these species. And then we see a third one. Oh yeah, sure enough, it's a really good estimate of this mutation rate. It's a nice linear thing, 3 mutations over a certain period of time. But notice now we get another mutation, and just by chance it happens at a site where there was already a mutation. So this ancestral T changed to an A right there. But then later there was a 4th mutation that changed the T, the ancestral T, to a C. But when we measure it, we still only count 3 mutations instead of 4 because we can't tell that there were 2 mutations that occurred at the same site. So that is called saturation. And so luckily for us, different parts of the genome evolve at different rates. So if I'm looking at one part of the genome or one particular type of genetic data, I might be in this saturation zone and not be able to accurately estimate, using a molecular clock, estimate these divergence times. But I could say, okay, we're saturated there, we see lots of diversity, so we won't trust it. Instead, let's look at this different part of the genome that's at a much lower mutation rate and is still on this linear curve and is still a very good estimate of divergence time. And then the only adjustment I would need to make would be for the different rates of evolution for these two different types of genetic data. Okay, so review that. Just make sure you know what neutral theory is and what we can use it for, and that although we might need to make adjustments, and so today sometimes it's called nearly neutral theory because we can adjust for some of these discrepancies and some of these variations we see if we have data sets that are big enough to allow us to accurately estimate those types of adjustments that we need to make. Okay. I'm not going to worry about this. If you're interested, there's some stuff in the paper for this week about why we don't necessarily need to correlate the amount of time that's passed with generation time, that it might actually be, we might actually be able to estimate real time like in years and decades and centuries rather than just in generations. But for our purposes,